Hi guys, so today we are going to look at transformations for one of the last functions of the year. So today we're going to look at exponential functions, which you actually have looked at in Algebra 1. So to start, like usual, we're going to look at what the parent function looks like. Except it's going to be a little bit different this time because we don't have one specific parent function like we've had in the past. The reason for that is the parent function actually will look different depending on what the base of our exponent is. So for what we'll do here is we'll just call it the base, okay, whatever the base is. The base is what actually is being raised to the exponent. So if this was 2 to the x, the base is 2. 4 to the x, the base is 4. So let's look at an example. All right, let's say, for example, we'll just call it base. If I were to plug in 0, if it was 2 to the x, or 4 to the x, or 10 to the x, whatever it is, anything to the 0 power is 1. So this graph is going to go through 0, 1. If I plug in 1, okay, 2 to the first, 4 to the first, 10 to the first, I'm going to get whatever that base is. If I were to plug in 2, okay, the base would be squared. If I were to plug in 3, the base would be cubed. So those values, so 0, 1, 1 comma the base, and then it's going to get bigger and bigger and bigger, multiplying each time by whatever that base is. So it's going to grow exponentially. You've probably seen this shape back in Algebra 1, so you're a little familiar with what it looks like. If I were to plug in a negative, remember what negative exponents do. 2 to the negative first would be 1/2. 4 to the negative first would be 1/4. 10 to the negative 10 would be 1 over 10. So it's going to be the reciprocal of that value, so it would be 1 over the base. If I did negative 2, it would be 1 over the base squared, so an even smaller negative number. So it's going to give my graph this sort of a shape. Now, if we think about those y values, no matter what x value I plug in, okay, 2 to the x, 4 to the x, 5 to the x, I'm never going to be able to get a negative number because I can't take a positive and raise it to any exponent and get a negative. Even though I can get really, really, really close to it, it's never going to touch it, so this graph is going to have a horizontal asymptote at y equals 0. So this is our exponential function. Now you'll notice specifically that I wrote that this is what happens when the base is greater than 1. Now we're looking at that case first for a couple of reasons. One, if the base were to actually equal 1, it would just be a straight line because 1 to the anything power is going to be 1. Same thing if the base was 0. 0 to the anything power is going to be 0. So neither of those would actually be exponential functions. Now the other problem is, let's say we look at a negative number. If I have a negative 2 to the x, that is actually not going to be able to be an exponential function. Because think about what would happen if I start plugging in values. All right, if I have negative 2 to the x power, well, negative 2 to the first would be a negative 2. Negative 2 squared would be a positive 4. Negative 2 to the third would be a negative 8. Negative 2 to the fourth would be a positive 16. So this graph is going to just bounce around like crazy to all those different points. Well, even worse than that, think about what would happen if I used a fraction. If I said this was negative 2 to the 1/2 power, now I'm taking the square root of negative 2. Well, that's not possible. It's not a real number. All right, what if I did negative 2 to the 1/4 power? Again, it's an even root of a negative. I can't do that. So there's going to be a ton of values on this graph that actually don't even exist. So when we look at exponential functions, we're only going to deal with positive bases. Now there's one other characteristic of the base we need to consider, and we'll look at an example here of a little bit, and that's when the base falls between 0 and 1. And we'll look at an example here in a little bit, and we'll also deal with this a lot next class. Now let's go ahead and find our characteristics on this function, starting with domain. That domain is everything. There is nothing that is going to stop this graph in terms of our x's. Range, however, is limited. We said we can't get those negative values, so my range is from 0 to infinity. It is a parenthesis on 0 because of the horizontal asymptote. This graph is increasing everywhere. It is not decreasing anywhere. This graph is positive from, I almost wrote 0. This graph is positive everywhere. It is negative nowhere. It does not have any symmetry. It does have an asymptote. There is a horizontal asymptote at y equals 0. And then end behavior is going to look a little different. As x approaches negative infinity, as those x's get smaller and smaller and smaller, those y's are getting closer and closer and closer to your horizontal asymptote, which would be 0. But as my x's get bigger, my graph is doing something different. As my x's get bigger, those y's are getting very large very quickly. So my y's are approaching positive infinity. All right, so now let's look at the same chart that you have seen so many times so far this year that you are probably very tired of seeing, but we only have it one more time after this, guys. You're almost there. And if I didn't last time, I've already filled in these words for you because you've seen them so much that hopefully you guys remember what they are at this point. So when it comes to exponential functions, you'll notice the way I wrote the equation, I put a capital B in there. That capital B is the base, because remember we said that base really could be 2, that base could be 10, that base could be a lot of different things. So depending on what that is, it'll change our graph slightly. I made it a capital B because we're so used to seeing the lowercase b as that horizontal stretch and compression. So with exponential functions, anything that occurs in the exponent is going to be your horizontal change. So in this case, if I have the base raised to the x minus h power, that would be a shift right. B to the x plus h would be a shift left. B to the b times x. So a number multiplied in the exponent would be your horizontal stretch or compression. And then a negative in the exponent would be a reflection over the y. All right, let's look at our shifts up and down. That's going to occur away from the exponent. So if I have a plus k over here, or a minus k, if I have a number multiplied out in front, or if I have a negative out in front, those are my vertical changes. Now, keep in mind, negative times the base to the x. That is not a negative 2 to the x. We cannot have a negative base, okay? Not the same thing. That negative is a reflection. Also commonly mistaken, that 3 is not a vertical stretch. If there's a vertical stretch or compression, there will be another value outside here, because that is not the same thing as 6 to the x, because that 2 does not have an exponent on it. We cannot combine those two things together. All right, also a little bit different on these graphs. Until this point, we've always kind of done our HK shift first. We've always kind of moved the vertex. We've moved the point of inflection. We've moved the starting point for square root. That HK point has been a really fundamental point of our graph. What's a little bit different if you think back to that parent function, so there's my asymptote, and here's my graph, that original function doesn't actually go through 0, 0. So until this point, every graph has, all right, well, except for rational, but that one was special on its own. So what we actually need to do here is that 0, 0 point, we are still going to move it. We are still going to look at the parent function in relation to that point. I'm calling that point the center of the asymptote. Now, it's not really the middle because asymptotes don't have middles, but it's going to be our new 0, 0. It's where our origin really has kind of shifted to. It's also where we're going to make our horizontal asymptote, which is a really important feature on the graph. So first thing we'll do is just identify some information before we actually sketch these graphs. All right, so if I have 7 to the x plus 1, I first want to determine what the base is. The base here is 7. Transformations. If it's raised to the x plus 1 power, it is shifted to the left, 1. The domain of every single exponential function is negative infinity to infinity. And then this graph has not shifted up or down. It's only shifted left. It's going to have the same shape as the parent function, so the range is the same as the parent function. There are two transformations that could affect your range. One of them is going to be a shift up or a shift down, because that will change where your asymptote is. The other change could be a reflection, because if my graph is going down, that's going to make my range look different. All right, let's try another one. So the base here would be 4. Okay, the 3 is actually a vertical stretch. And then the minus 5 is a shift down. Domain, again, negative infinity to infinity. Because it's shifted down 5, though, that means that the horizontal asymptote is now at y equals negative 5. That means that the range is going to be from negative 5 to infinity. All right, and then finally, I have a base of 3/4. That 4 up there in the exponent is a horizontal change. Specifically, that is a horizontal compression. And then that plus 1 is a shift up 1. Domain has not changed. Range, because it's shifted up 1 and it has not been reflected, is from 1 to infinity. Now, if there was a negative out in front there, it would be from negative infinity to 1. All right, so let's go ahead and actually sketch some graphs now. So let's start with the first one, okay? Again, first thing I'm going to do is identify that HK point we talked about. So this graph, let's see where we've shifted. We've gone left 3 and down 1. So until this point, usually, again, negative 3, negative 1 would be a point on my graph. -3, -1 isn't actually a point. What I'm going to do is put a little x there, or a little star is what I usually do. So we're still going to look in relation to this point for my parent function pattern. So that parent function is still going to have a similar pattern from that point because it is my new 0, 0. Parent function for exponential is 0, 1 because anything to the 0 power is 1. 1 comma the base. In this case, the base is 2. So 1, 2 is what the parent function would do from the origin. 2, 4. Because it would be 2 base squared. If you wanted to, you also could do -1, 1/2. Now you don't need to, you probably have enough points at this time, but if you want to go ahead and do another one, it's not a bad idea. All right, so then at this point, what I would do is I would go ahead and look at my stretches, compressions, reflections like I usually do. So this graph has been reflected over the x-axis. It has not been stretched. The 2 is the base. We took that into consideration when we made our parent function points. So since it's been reflected, it's going to make those values negative. So that's where we're moving from that little star point that I made. That little star point is not actually on my graph. It's just where we've shifted our 0, 0. Now, the other important thing to keep in mind, wherever we make that star, that is the location of your horizontal asymptote because that's what was originally at 0, 0. Now from that point, I'm going to go over 0 and down 1. I'm going to go right 1 and down 2. I'm going to go right 2 and down 4. And I'm going to go left 1 and down 1/2. And then I will have the shape of my parent function. Domain, again, for all of these is -infinity to infinity. But my range here, bottom to top, the lowest y value is -infinity. And then it goes to -1. All right, let's try another one. Again, whenever I have a value in front of that x, I want to go ahead and factor it out. So this will become x minus 6. So what I'm going to look at here then, my shift would be at 6, -4. So I'm going to go to 6, -4 and put that little star, which means that is where I'm going to put my horizontal asymptote. The parent function pattern for an exponential would be over 0, up 1, 1 comma the base, 2 comma the base squared. Let's look at stretches, compressions, and reflections. Well, at this point, we have a horizontal stretch. So multiply those by 2. So from that little star point, over 0, up 1, right 2, up 3, and right 4, up 9. Which is a little bit off my graph. And I have my exponential function domain. Again, all of these is going to be the domain. My range would be from -4 to infinity. All right, let's try a couple more. So on this next one, if you feel pretty comfortable, pause the video, try this one on your own. All right, let's see. This graph has shifted down 0 and, sorry, not down 0. Well, yes, down 0. It's gone up 2 and left and right 0. So my new HK point is going to be 0, 2. So from 0, 2, I'm going to put a little star, and I'm going to make my asymptote. So from that point, parent function pattern, over 0, up 1, 1 comma the base, 2 comma the base squared. Stretches, compressions, and reflections. So times a -1/2. We also have a reflection over the y, which is going to make those values negative. So from that star point, over 0, up down 1/2, left 1, and then down, that's some bad multiplying. I just wrote -1/2 instead of actually multiplying by 1/2. So that would be down 2 and down 8. So left 1 and down 8. Sorry, wow, can't read my writing. Left 1 and down 2. There we go. 1, 2. Left 2 from that star and down 8. And that is my exponential function. Domain is from -infinity to infinity, and my range as, almost wrote end behavior. Wow, guys, I'm struggling today. Lowest y value is -infinity, highest y value is 2. Again, it does have a parenthesis because it does not touch it, because there is an asymptote at that point. All right, so this last one is going to be an example of what happens when that base is actually less than 1. So in that 0 to 1 range, or 0 to 1 range. So let's go ahead again, identify what the base is. Okay, the base is 1/2. It's what's being raised to the exponent. Let's find our shifts like we're used to. We've gone right 2 and down 4. So 2, -4 is that little star point that these points will be in relation to. It's also the location of the horizontal asymptote. So from that point, the parent function pattern is still 0, 1. It's 1, comma, the base, which is 1/2. It would be 2 base squared, which would be 1/4. Well, to see this a little better, let's use some negatives. If I do -1, 1/2 to the -1 would flip it and become 2. If I did -2, that would flip it and square it and become 4. So you don't need this many points, but I do want you guys to see this many in this case, just so you can see what happens to this graph. Now we do have a vertical stretch that I'll go ahead and apply. And then let's go ahead and make those moves. So over 0, up 3, right 1, up 1.5, right 2, up 3/4, left 1, up 6, and then left 2, and up 12. So you can see what's actually happened to this graph. In comparison to the parent function when b was greater than 1, it looks like it's a reflection over the y. All right, so a base less than 1 is actually going to have a change on the shape of your graph. And again, if you think about it, it's because 1/2 to the x is the same thing as 2 to the -x. That's why it looks like it's a reflection over the y. All right, guys, so that is it for transformations. You've got some practice in your learning journal as well as a Desmos activity to get done for today.